Hi everybody, today we're starting antiderivatives. So let's start with what is that, what is our definition? So f of x, and notice this is a capital F of x, is the antiderivative of a lowercase f of x if when I take the derivative of the capital F of x, I get the lowercase f of x. So the two things are related. When I take the derivative of the first one, I get the derivative of the second. So let's do an example just to kind of get a feel for that. So here I have f of x is equal to x squared plus 3x minus 2. And notice that was capital F of x is x squared plus 3x minus 2. And you should know by now, right, that when I take the derivative of that, derivative of x squared is 2x, derivative of 3x is 3. So you can see that when I took the derivative of capital F of x, I got 2x plus 3, which is what my other function, lowercase f of x, is equal to. So this is the relationship between these two functions. A little bit more to go with that though is that really unique? Like, is this capital F of x the only function whose derivative is 2x plus 3? So I wrote a couple other functions to show you here. So here's our original x squared plus 3x minus 2. And then I did a capital G of x, which is x squared plus 3x minus 5. And notice when I take the derivative, I get 2x plus 3. Same thing here with this capital H of x is x squared plus 3x plus 750, and if I take the derivative, I get 2x plus 3. What is difference between capital F of x, capital G of x, and capital H of x is the constant. I had -2, I had -5, and I had 750. We should know by now that when you take the derivative of a constant, it's 0. So you're not seeing that constant when I take the derivative. So it's important that we kind of look at that constant, that -2, the -5, the 750, and we're going to acknowledge that that's going to happen. We're going to have this constant that might be there, and maybe it has different values. So what we're going to call that is C, and I'm going to use capital C so you can tell what I'm doing. And it's just going to stand for a constant, and we call it the constant of integration. So it says when we do this thing called integration, which is the same thing as doing the antiderivative, there could be an unknown constant, and we're just going to say, we're going to throw that C in there just to keep track of it. So let's look at some notation. I have the antiderivative of lowercase f of x is written as, so you see this kind of curly sign, so that's our integral sign. And so I have the integral of f of x dx is equal to capital F of x plus c. So we're saying when I take the antiderivative of the little f of x, I'm going to come to the big F of x. Here's our note that we started with. When I take the derivative of capital F of x, I get lowercase f of x. This will get better as we go. It's new at first, so it takes a little while to get used to. Think of this integral sign here, along with the dx, as being a pair. So every time I have an integral sign, I need to have d something. It could be dx, dy, dt. It doesn't matter. That'll be given with the problem. But they have to be given together. So we say when we do this thing called integration or the antiderivative, we have to say, what variable do I have? Because we're not always going to write f of x, right? We'll have some functions and some stuff written in there like an expression. So I need to always say, what am I integrating with respect to, so that dx or d whatever says, here's the variable I want you to use. I'll try to mix it up a little so we see that. Our first rule and our big rule is the power rule. So we had power rules for derivatives, so now this is the power rule for integration. So I have the integral of x to the n dx is x to the n plus 1 divided by n plus 1, then plus c, where n is not equal to -1. So let's talk about that. When I did derivatives, I brought the n down and I subtracted 1. I want you to think of antiderivatives as the opposite. So we're trying to come up with the original function given the derivative. So the opposite of bringing a number down would be bringing the number up, right? So I'm going to increase it. So the n minus 1 that we used to do, now we're going to do plus 1. We used to bring the number down, which was multiplying. So what's the opposite of that? It's dividing. So whatever I have as my power, add 1, divide by the same power. So you will see this match between the n plus 1 as the new exponent and the n plus 1 in the denominator. That should help. n is not equal to -1 because think about, if I have -1 plus 1, that would be 0. And then I would be saying divide by 0. So I would have like x to the 0 divided by 0. And we know that's a big like no in math. We never divide by 0. So we're not going to use -1. So let's do multiple examples of what this looks like. So the first one I have is the integral of x cubed dx. So I said, okay, my power is 3. Let's raise it 1. So I raise it 1. That's to the power of 4. I divide by the same thing. So those two match, and I say plus c. Let's keep in mind, what are we doing? We are finding a function whose derivative is x cubed. So you could check this. You could say, hey, if I take x to the 4 divided by 4 plus a constant, and I take the derivative, what would I get? It may help to say, well, that's 1/4 x to the 4th plus c, and we're taking the derivative. So the 4 would come down, which cancels the 1/4. You would get x cubed. The derivative of c is 0, so you can see I got what I started with. That's what you want to do. The whole idea of the dx is if that had been like a y, say I had y to the 4th dy, then that time I would make the power of y go up to 5. I would divide by 5 and I would add c. So just think of this as a check, and I'll make sure we talk about that more. So we want to practice this over and over, so I'm starting really simple of let's just do this repeatedly. So the integral of x to the 6 dx, I add 1 to 6, which gives me 7. I divide by 7 and I add c. You have choices of how to write this. If you would like to write this as 1/7 x to the 7, that's completely okay. It's just a matter of preference, really. So if you like to see the fraction separate from the x, then you can choose to write it that way. When I look at x to the 8th dx, I take the integral, which means I add 1 to the power, that's a 9. I divide by 9 and I add c. Of course, we're going to come along some that aren't as pretty and aren't ready to be integrated right away, so you have to rewrite. So this one that says 1/x to the 5th, I want to write that as a power, so my power is -5. Slow yourself down enough to remember negatives kind of go backwards. So when I add 1, it becomes -4, divide by -4, and add c. So remember, I think you're going to want to start going, oh, 7 went to 8, and 8 went to 9, and 9 went to 10, so -5 will go to -6, and then you say, wait a minute, negatives are a little backwards, and I don't want to do that. As far as notation goes, you could choose to take this x to the -4 and put it back into the denominator, which will be +4. This 4 that was in the bottom would stay in the bottom, and then that negative, I would put it in the numerator. What did we say? This is a choice, so you can choose which way to do it. I just want you to be aware when you see answers, if you're like, where did that -1 come from? It was just a rewrite. Let's look at some more that we would want to rewrite, like the square root of x. Well, remember, the square root is the half power. When I add 1, 1 plus a half is 3/2. Now you're going to divide by 3/2 and add c. This one, you do need to rewrite it. This is a complex fraction. So I have a fraction in the denominator, which is really not what we like to see. So when you divide by a fraction, you multiply by the reciprocal, which means it turns over. So I have, instead of divide by 3/2, multiply by 2/3, and then you have x to the 3/2 plus c. Do you see again how you could check this with the derivative? If I take 2/3 x to the 3/2 plus c, and I take the derivative, you can see 3/2 and 2/3 are going to cancel. So you would have x. When I do 3/2 minus 1, I get a half, and the derivative of c is 0. So I can see that I could get right back to where I started if I decide I want to check it. I wanted to do a second one kind of like that. This is the cube root, which means I have x to the 1/3. So there's my integral of x to the 1/3. So again, I add 1. 1 plus a third is 4/3. And I do say you do need to write it as a fraction. Don't try to do a mixed number like 1 1/3. You'll never see it written that way. I divide by the same number. So the same exponent goes in the denominator, always plus c. I'm going to flip that 4/3 over. I'm going to flip that 4/3 over. It's going to become 3/4. I have x to the 4/3 plus c. As far as the exponent goes, you can leave it that way. I would leave it that way if you wanted to see what else it would look like. It is still the cube root, but the power inside is now a 4 plus c. I think I would leave it here as this first one, but you can write it either way. Right. Of course, there are more rules, but these rules are kind of nice and I think kind of intuitive. I think you would do it even if I didn't talk about it. So the first one is just what happens with a constant. So if I have this constant that is being multiplied by the function, so it's a coefficient. So I have the integral of k times f of x dx is equal to k times the integral of f of x dx. What does that say? What does that say? It says if you have a coefficient, you're just going to hang on to that coefficient. You're not going to do anything with it. You're just going to keep multiplying. Then I have the integral of f of x plus or minus g of x, saying if I'm adding or if I'm subtracting, I'm going to do the same thing. I could look at the integral of f of x, then I could add or subtract, whichever one I'm doing, the integral of g of x. So it's kind of like I can look at each piece one at a time, which is nice. Then the last one is just a specific version or type. The last one is a specific instance of the power rule because I just have a constant dx. So this constant, I'm going to give it an x. What does that mean? So it's kind of like I had k times x to the 0. Remember, x to the 0 is 1. So this k, I'm still doing the power rule. It says my power was 0, so add 1 to it. Divide by 1, so I would just get kx. I think it's really helpful to just think of this when you have k, give it an x. In general, I also think about integration as passing out x's. So whatever power you have, give it another one, right? So that's what I'm thinking. When I'm looking back at my function, I should see the power has gone up. So let's do a few more integrals with these new rules. So the first one I have is 8x cubed dx. So I keep the 8. X was 3. I make it power 4. I divide by 4. I add c. 8 and 4 cancel. That becomes a 2x to the 4th plus c. The c needs to be just, you don't even think about it. You add it every time to say it could be there. Again, you could check this. If I take the derivative of 2x to the 4th plus c, 4 comes down. 4 times 2 is 8. I subtract 1 from the power, so now that's a 3, and the constant goes away. So I'm right back where I started. That's the goal. Get back to where you started. This should feel circular. Try again. I have 3x squared plus 4. So here I have two things. So let's look at the 3x squared first. 3x squared, increase the power to 3, divide by 3. The 4, all by itself, I give it an x. That's what I want you to think with the constants by themselves. Just go ahead and give them an x, and then I have my plus c. You do want to cancel, make it a little bit better. The 3's cancel. I have x cubed plus 4x plus c. And again, check it. X cubed derivative is 3x squared. 4x derivative is 4. C goes away. Let's do one where the numbers aren't as pretty. So I have the integral of 5x squared minus 7x minus 9 dx. So I have the 5x squared. I'm going to increase the power to 3, divide by 3. 7x, I'm going to go from power 1, and you may want to write that in there because this is new. Power 1 goes to power 2, divide by 2. The 9 becomes 9x, and then you have plus c. So I have 5x cubed over 3 minus 7x squared over 2 minus 9x plus c. That's perfect. Leave it alone. Let's throw one a little bit different. I have the integral of a half of x plus 6 over x squared dx. Rewrite that. I'm going to leave it as a half of x. Maybe write it as a power 1. I think that's helpful. And then let's say this is 6x to the negative 2 to write this as a power rule. So the 1/2, leave it alone. X, raise it to the power 2, divide by 2, plus 6x, now raise it, it's -1, divide by -1, add c. This can and should be simplified. So this 1/2 times x squared over 2 becomes x squared over 4. I just multiplied 2 by 2. The 6x to the -1 over -1, this negative overall says let's subtract this in between. The 6 I'm going to keep, and the x to the -1 I'm going to write in the denominator, and then plus c. You could, of course, check it like always. I'm going to stop the checks for a minute because it just makes the video too long, but I want you to see, break it down to little steps and it won't be too bad. This next problem, and I actually wrote it kind of twice, shows you why I have to write dx or dy or whatever I want you to use. So when I look at the integral of 5 dx, remember it's a constant, I'm just going to give it the x plus c. If instead I had written the integral of 5 dy, then y is what I'm integrating with respect to, and I would want to write 5y plus c. So that dx or that dy is really important so I know how to integrate what I'm given. I'm going to continue to make this a little bit bigger. I want to throw in some multiplication and division, and there's kind of like good news. There's not a lot of rules for integration for business calculus. If it's another kind of calculus, you may have more rules because you have trig and stuff, but for business calc, we have these nice little things that we do. So there's not a product rule, there's not a quotient rule. What you need to do is simplify. So I'm going to multiply x times x minus 5. So I'm going to have the integral of x squared minus 5x dx. Now I can apply the power rule. So this is x cubed over 3 minus 5x squared over 2 plus c. It's important that you first multiply before you integrate. You would not get the same thing if you tried to integrate first and then multiply. So simplify before you use the power rule. Here I have 12x plus 6 over 3x cubed. So this time I want to divide. I'm going to write it the long way. 12x over 3x cubed plus 6 over 3x cubed and then dx. All right, so simplify some more. 12 divided by 3 is 4. This is x to the power 1 over x cubed. When you divide, you subtract exponents, so I have x to the negative 2. Same thing for the 6 over 3x cubed. 6 divided by 3 is 2. I have x to the negative 3 dx. Now, I haven't integrated yet. The powers changed because I divided, so now let's go ahead and integrate. So I have 4. X increases by 1, so it's negative 1, divide by negative 1. The 2, x to the negative 3, I add 1. Negative 3 plus 1 is negative 2, divide by negative 2, add c. This could simplify a little bit more. 4 over negative 1 is negative 4. The x to the negative 1, I'm just going to write that over x. 2 divided by negative 2 is negative 1. And the x to the negative 2, I'm going to change that to x squared and say plus c. So it's lots of little steps. It's nothing too big just yet. Here's another one to multiply, x minus 4 squared. So let's first start by saying x minus 4 squared is x squared minus 8x plus 16 dx. When you square a binomial, you get a trinomial. I used a rule there, so I said x minus 4 squared. I knew to square the first term, I knew to square the last term. I multiplied x times negative 4 times 2, I got 8. If you don't remember that, which is perfectly okay, you write it out. So you can say x times x is x squared, then you have minus 4x, and then you have minus 4x again, and then you have negative 4 times 4 is 16. So I used a shortcut. Now you can integrate. X squared is x cubed over 3. 8x is 8x squared over 2. Remember it was a 1. I add 1, divide. 16, you just give it an x plus c. So look at all the powers went up. 2 went to 3, 1 went to 2. This didn't have an x, so I give it 1. One little piece could simplify, so I have x cubed over 3 minus 4x squared plus 16x plus c. So I put a couple in here for you to try, and my idea is you try it without me talking. So you pause the video and you try a couple to see if you're getting it before we go on to a few more rules. When you're ready, you come back and watch, see how you did. All right, so I'll start with the 4x minus 7. I'm going to make that 4x squared over 2 minus 7x plus c. One little step of simplification, I have 2x squared minus 7x plus c. For x cubed plus x squared plus 8x plus 2 dx, I get x to the 4th over 4 plus x cubed over 3, 8x squared over 2 plus 2x plus c. Again, one little step of simplification, x to the 4 over 4, x cubed over 3, 4x squared plus 2x plus c. One last u try. I have this is 8x to the negative 5 dx, so always rewriting to make it a power rule. Now this 8x, when I add 1, it becomes negative 4. I divide by negative 4, I add c. 8 divided by negative 4 is negative 2. Then I have x to the negative 4 plus c. You can also write that as negative 2 over x to the 4th plus c. A couple more rules that we need to talk about are rules for e to the x and 1 over x. Remember earlier I said the power rule x to the n works when n is not negative 1, so we have to say, well, what happens if we have negative 1? What are we going to do? So the rule for e to the x is the integral of e to the x is e to the x plus c, which is nice. E to the x, when I took the derivative, was still e, so when I integrate, it'll still be e. The rule for 1 over x is it becomes natural log, and hopefully you remember when we took the derivative of natural log, we got 1 over x, so we want to pay attention to that. When you take the integral of 1 over x, though, we call it the natural log of the absolute value of x plus c. So this is because we can only take the natural log of a positive number, so we want to make sure we have something that's correct when we go to maybe put a number in later. So the absolute value is there. It's not the biggest deal to me in the world that you do it, but I will write it because it is technically correct. So let's try a few examples of that. Let's start with 4e to the x dx. It will be 4e to the x plus c. Nothing big happened. Even if I make it bigger, so I have the integral of e to the x minus 3, it will be e to the x. The negative 3 is going to pick up an x, and then I have plus c. So the power rule is still there for things that are not e, but e to the x just stays e to the x. 2 divided by x. Let's rewrite that as 2 times 1 over x. I think that's helpful, maybe to separate the 1 over x. That way you'll see, oh, 1 over x, that becomes the natural log of x. I'm supposed to put in an absolute value, so I'm going to. If you have a hard time picking up on the 1 over x, because I know this is all new, I think you'll see it anyway, because if you tried to make this 2x to the negative 1, you're going to get to the part where you write 2x to the 0 and you divide by 0, and you're like, oh, I can't do that. So you should be able to catch it. When you catch yourself, you're like, yeah, that's right. There's a special rule for 1 over x. It becomes the natural log. There are some fun rules with natural log that can be used to write this differently. So I want you to see other ways this could be written as the answer. Remember how there was that rule that the natural log of m to the p is p times the natural log of m? Well, that could go forward or backwards, right? So written this way with the 2, if I wanted to, I could bring that power up and make it x squared. Then x squared is always positive, so you could just drop that absolute value and call it plus c. This is not a hard and fast, like you have to do this, but I want you to know it might be done. You may see this happen. You may see this written different ways, so I don't care which way you do it, like they're both the right answer, but I want you to see this is a choice, is to bring that power up. So let's try that a little bit more and like start to see when this is going to occur. So I have the integral of 6x plus 3 over x. We need to divide 6x over x, 3 over x, dx. The 6 over x just becomes 6, and I'm going to again separate 3 and 1 over x. So integral of 6 is 6x. I have the 3. I have the natural log of the absolute value of x plus c. Now this time, if I bring the 3 up, like this is just to show you how this would look, I would have the natural log of x cubed. I would still have to have the absolute value because I don't know if x cubed is positive or negative. It could be either. So you only get to drop the absolute value when the power moves up and it's either. Right. The next one says the integral of e to the x plus x over 2. I'm going to rewrite that as e to the x plus a half of x dx. I just want you to see the half separated from the x and put the power of x as 1. E to the x will stay as e to the x. I'm going to keep the half. X is going to become x squared over 2 plus c. So I have e to the x. The half with the x squared over 2, we can make that x squared over 4 plus c. Now let's check out this 1 plus 1 over x plus 1 over x squared plus 1 over x cubed. Again, a rewrite will help us. I have 1. I want to keep the 1 over x plus, I'm going to make this x to the negative 2, x to the negative 3 dx. The 1 just becomes an x. The 1 over x is natural log of the absolute value of x. X to the negative 2 becomes x to the negative 1 over negative 1. X to the negative 3 becomes x to the negative 2 over negative 2 plus c. I can make this x plus natural log of absolute value of x. X to the negative 1 over negative 1 is negative 1 over x. X to the negative 2 over negative 2, I can make that x squared go to the bottom. The negative 2 stays there, but I'm just going to move it up to the top so I can make that x, natural log of x, minus 1 over x, minus 1 over 2x squared, and then, of course, plus c always. We do have times that we can solve for the c, and the only way we can do that is if we know an initial value of f of x. So let's try one. We're going to find f of x if we know that f of 2 is 9 and f prime of x is 4. So we're going to integrate the 4, right? That's our derivative, so that'll get us back to f. We're going to integrate our derivative. That'll help us find f of x. I'm going to write it right here. F of x is equal to the integral of 4 dx. That will be 4x plus c. We still have a c right now, but we know that f of 2 is supposed to be 9. So if I do 4 times 2 plus c, I'm supposed to get 9. Well, 4 times 2 is 8, plus c is 9, says c is equal to 1. So this one, we have f of x is 4x plus 1. Let's try that again. We're going to find f of x. This time f of 0 is 3 and f prime of x is 2x minus 1. So to get f, I'm going to integrate 2x minus 1 dx. This is going to give me 2x squared over 2 minus x plus c, and this is f of x. F of x is equal to x squared minus x plus c. But I just said f of 0 is supposed to be 3. So 0 squared minus 0 plus c is 3. I can see c is 3. So my function f of x is x squared minus x plus 3. Let's try that with a different notation. So here I have dx dt is 2e to the t plus t, and x of 0 is 12. We want to find x. In this notation, I am integrating, and that integration will give me x. So I'm going to get x. I have 2e to the t plus t, and this is going to be dt. So I'm integrating with respect to t. So 2e to the t is still 2e to the t. T is t squared over 2, and this is going to give me x. Remember, I have plus c. C is what I'm trying to figure out. So this says if I plug in 0, so this will be x of t. X of 0 is 2e to the 0 plus 0 squared over 2 plus c, and that says that's 12. E to the 0 is 1, so 2 times 1, this is 2. 0 squared over 2 is 0, so I have plus c is 12. I can see c is 10. So x of t is going to be 2e to the t plus t squared over 2 plus 10. Let's try that kind of notation again. I think it's good to repeat it. So this time I have dy dx is 3x squared minus 6x, and y of 1 is 25. Let's find y of 4. So to get y, I'm going to integrate 3x squared minus 6x dx. This gives me 3x cubed over 3 minus 6x squared over 2 plus c. Now I have x cubed. I have minus 3x squared plus c, and this is my y. Let's call it y of x. So y of 1 is going to be 1 cubed minus 3 times 1 squared plus c, and that's going to be 25. I have 1 minus 3 plus c is 25. 1 minus 3 is negative 2. Negative 2 plus c is 25, says c must be 27. This time, as I'm plugging it back in, I want to do y of 4. So y of x was x cubed minus 3x squared plus 27. So I have y of 4 is 4 cubed minus 3 times 4 squared plus 27. This gives me 43. So let's take a look at that with some business applications. So I have the marginal revenue is given by r prime of x is 0.25. Find the revenue function. So to start off, I want to remind you that r of x is 0. So if I sell 0 objects, then I have made $0, and that will never change. There's cost, right? You can have a cost when you sell nothing. You can have a profit, which would probably be a loss if you sell nothing, but revenue for 0 is always 0. So this should say r of 0 equals 0 instead of r of x. Remember, r of 0 is 0. So we're going to integrate. To get r of x, I have 0.25 dx. Well, that's going to become 0.25x plus c. We know r of 0 is going to be 0. So 0.25 times 0 plus c equals 0. That says c is 0. So our revenue function is just 0.25x. In the next one, I give the marginal cost is given by c prime of x is 0.02x plus 4, and c of 0 is 2500. We want to know the cost of 100. So I'm going to integrate 0.02x plus 4 dx. And that'll give me my cost function. So I have c of x is 0.02 x squared over 2 plus 4x plus c. This 2 will cancel, so I have 0.01 x squared plus 4x plus c. Luckily, I gave you 0, so 0.01 times 0 squared plus 4 times 0 plus c, saying 2400, just says c is 2400. So I have a cost function of 0.01 x squared plus 4x plus 2400. So let's find the cost of making 100 items. 0.01 times 100 squared plus 4 times 100 plus 2400. And this says the total cost for 100 items is $2,900. Here's our last one. The average marginal cost of x items is given by 4x plus 24 over 2x. And the average cost for one item is $35. We want to find the cost function. So I'm going to start by integrating the average marginal cost function, and that way I can just get the average cost function. I can simplify this. 4x over 2x is just 2. 24 over 2 is 12, and that's over x. So I'm going to write that one more time. I'm going to make that the average cost is equal to 2 plus 12 times 1 over x dx. Right, so my average cost, the 2 gets a 2x. I have 12 times the natural log of x plus c. I'm plugging in 1. So I plug in 1, and it's supposed to give me 35. So plug in 1, I get 2 times 1 plus 12 times the natural log of 1 plus c. Now the natural log of 1 is 0, so 12 times 0 is still 0. So this says that 2 plus c is 35, so c is 33. Okay, so now I have the average cost is 2x plus 12 times the natural log of x plus 33. The original question says find the cost function, so not the average cost, but just the cost. So remember, average cost is c of x over x. So if I do x times the average cost, I'll get back to the cost function. So I'm just going to take this cost function and multiply it by x. So I have x times 2x plus 12 natural log of x plus 33. This says I have 2x squared plus, I'm going to write this as 12x natural log of x, and then plus 33x. You can't put the x and the ln of x part together, like that won't become x squared. These are separate. All right, so this was our first look at integration. We will have many more lessons on this, so we finish off the semester. I hope this helped.